What is wave-particle duality? In part, this comes from the basic fundamental forces. And in part, the world as it gets smaller gets really simple, although strangely enough, as I show, it will become complex once you get it back together again, and that it's not so easy to make it things. But what I'm going to talk about is three fundamental fields or forces or interactions or accelerations, depending on what level you're talking about. So there is the radial electrostatic charge. That is isotropic, which is a fancy word for saying the same in every direction. It's based upon the charge. There's a separate force that's the extra 1 over r called the radionucleostatic, which I relate to the strong nuclear force. This one is 1 over distance squared, and this one is 1 over distance cubed, an extra 1 over r. And of course, when you have those two, there's some point that it balances. And for the 1 proton, 1 electron hydrogen atom, that is the Bohr radius of hydrogen. And you'll find that throughout this physics. And we call that A sub O is the number for it. So the red arrow, electrostatic, the green solid arrow is the strong nuclear force. Now, these two affect in every direction. So it really pulls the whole particle. However, the axial nucleostatic, which I relate to weak nuclear force, okay, is not in that direction. It's towards the nucleostatic axis of the nucleus. And really there is an axis of every particle, but there's so many count here in the nucleus that its field is the strongest. And this doesn't go in this direction, but it goes depending upon a theta, an angle, an inclination angle from the poles. Or if you like to think of this in hemispherical coordinates, that's a longitude from the equator. But since the axis is on the poles, I use inclination angle, not its complement. So this is the basic three fundamental fields in the world, in the universe. Now, the problem is once you have that field, particles become more complex. You see, they can change, they can rotate, they can move. And so if you have that axis, it can go. And if it's going over and over, that axis is changing its strength based upon what looks like a sine wave, a wave function. Yet there are other times, if it's rotating this way, the poles are pretty much staying in one place and you get no. And so you get some invisible, the letter I function, because somehow that energy disappears, at least for the moment you're thinking about. Or there's some combination in between that sort of looks like a spinning top, where it's rotating this way, but the axis is moving also. So in part, something so simple as one axis can become complex because of time, rotation, and physical movement. You're going to have to take all three of those into account as you learn advanced subatomic physics. Well, let's see how this works. So I'm going to look at this from the equator view, okay, with the axis of the nucleus is the main one. So here's the nucleus, and there's one of these electrons. Now remember, there's also another electron at the 180-degree position, because that makes it very balanced in a Newtonian uh, um, section. And so there's a negative, and then the matching positives in the middle, so that once you get beyond the system, it is a balanced system. Okay? Now, so what we'd like to do is then to see this electron has an axis and the nucleus has an axis. So in real life, what happens is this electron wants to move onto that axis as linear movement. But that electron also wants to rotate its axis so it's pointing towards the big one here in the nucleus. So you're getting linear movement and rotational movement. Similarly, back here at the nucleus, it wants to move all the way up to that axis of the electron. But also, it can rotate its axis. And then there's, of course, this matching one over here. So three fundamental forces, a frame of reference axis, and both linear and rotational of this item causes the simplicity of just particles to become these complex systems that we have to study in subatomic physics. So for example, here's the static equation for electrostatic potential. There's potential, there's force and acceleration, and there's fields. So typically, this is K over R. Obviously, the force was K over R squared, and the field is K over R cubed with the appropriate scaling as you do the derivatives and or integrals to move between the different layers. Now, this Coulomb concept is nice, but it's mixed. I've also seen it displayed as this permittivity of space factor with this 4 pi. But what I did in one of my early papers was I converted this, and I've got the charge numbers over the standard charge, and I've got that 2 pi with this conversion, and then eventually it comes down to Planck's constant times the speed of light, this h hat c constant, times this fine structure constant, which really isn't a constant, it is a scaling factor, times the number of charged particles, not the charge. And again, then times this relationship of how strong that field is as you move away. Okay, so instead of using these abstract mixed constants, I've separated into things that we know are fixed. This Planck is relative to the standard at the Bohr radius, okay, where both fields, the radial electrostatic and the radial nucleostatic, the strong nuclear force, are in balance at the Bohr radius. So they're both the same. And the value of the strength plus and minus at the Bohr radius, A sub O, is that number. So you'll see this number all the time. And in my work, you'll see me doing not the fine structure constant, but the equilibrium versus edge scaling factor. It's the same number, but by using my naming, you'll actually understand the 3D engineering that's actually happening here. Okay, so what happens is that Planck H hat C at Bohr. H hat C is always at Bohr, but you have to strengthen it up in the field, go up that curve until you get to the particle edge, which is the maximum. And so this is the conversion to make H at C into charge. That's the units of measure at the particle edge. Then all you do is you have the count of how many charged particles and how many charged particles, and we don't have to have charge. As you'll see later in my courses, I also have a way to eliminate variable mass using a similar position in a field evaluation that will get rid of all the complexities of trying to figure out rest mass and variable mass and get back to simple things like always HC, but referencing it at AO. Okay, so what's the radial nucleostatic, that extra 1 over R equation? Well, let me do it at the force level because most of us are more familiar with that. So the one we had from the last is the force of electrostatic, okay, is this ratio. And again, for force or acceleration, it's R squared. But the force for nucleostatic is an extra 1 over R. okay? And but that has to be relative to that Bohr radius, A sub O. So the force, balancing force, has an equation, looks exactly the same, except when the radius of A sub O, it will be the same, but when the radius is something else, it will not be. In fact, it actually always, for the hydrogen, comes back to that radius. Further, there is that weak axial force. So that takes that same force, but you're going now effectively back here as if you're going to every point on this line. Now, the thing is, these are in this direct, these are in negatives, and those are positive, so they cancel each other. So there's really like a triangle here. So if you get this times that, that's the cosine times the sine. That is the strength of the nucleostatic sine times cosine relative to that strong nuclear force. The weakest sine times cosine is always less, and can be very much less. And that's why they call this the weak nuclear force. And I call it the axial because I want to get in the 3D geometry that helps make everything good. Now, even more importantly, I don't like equations that are just um, giving you strings or giving you numbers. This is how we've gone. You really have to translate this into a hemispherical coordinate system. How much is it from the radius? That's the pole particles part. How much is it relative to the angle you're at? And then how much is it at the latitude, the inclination angle or the longitude? And the phi here is the latitude. In that case, you actually multiply this times the sine and that times the cosine, and basically you get a radial part, a axial part, um, axial part, and there is no balance. You can go around this system and nothing will happen at the same. And that's why at the same latitude, you get this ring of electrons that becomes an electron subshell, because a whole bunch of electrons follow this and stack themselves up as best as they can based upon this third equation. Now, again, we're trying to go from very simple concepts. I thought we had an axis, which gives a wave function, and a whole particle, which comes from the radial surfaces that don't change based upon angle. However, it's more than that. You see, if you have an axis, you actually have this r sub e distance out of the particle, and you have two poles. Now, these are not north-south poles. These are both repulsive between the electron, say, and a central neutron, or the nucleus, okay? So you'll have, but those are different. There are two poles, not a monopole like Dirac said, but with the same math, because you have to remember there's two of them. So they may pass twice. If you have one rotation, they pass twice. So you'll see in advanced physics a 720-degree cycle. Well, that's really the two poles passing one rotation, but you see it twice as often. So they did the abstract math as if it was 720, instead of understanding that it's two Dirac monopoles, but located at 180-degree positions at r sub e, that radius of the electron that we used in the previous equations. So these also come in these other systems. As I said, electrons want to be at this 180-degree position. They're pulled in up to a wall at the Bohr radius, but they want to be as far away from each other as possible. So in almost every case, you will find electrons really forcing themselves to be at 180 degrees in pairs. But this is not like a Lewis diagram in our current textbooks. This is really a pair at the very far position. And finally, this complexity that I talked about becomes these electron subshells. You see, at that longitudinal ring or that inclination angle, you can get multiple sets of them. The electrostatic between the proton and the electron is attractive. The strong nuclear force between that nucleus, that electron and the nucleons is repulsive, and you get some sort of a balance in the radial direction. You also have this weak nuclear force pulling it towards the axis, but you have a set of other electrons, and guess what? They all balance. And that becomes a repulsion in the axial direction. So two in balance, and you get what's known as the Bose cylinder surface, and then in his paper, and then he also said, but I have to multiply two to make the equations work. And so he said, that seems like polarity. And the polarity is really this polyhemisphere pair sitting at 180 degrees relative to the nucleus, because that way you have a negative and a negative with the central positive, so that beyond localization, this is a balanced system, not and no drift, no electric dipole in the broadest sense. Now, this leads you to all three of these in this example want to fall in there, but guess what? They bounce off of each other in units of electrons, quantization. So now you have an electron interaction that is a bouncing. It can only be in single units. It's not like it's evenly distributed. Now you'll see electron distributions that look like big longitudinal um, rings, okay? But that's because they can't tell where they are, as I said, because that phi is in every direction. And then eventually you get what is quantum numbers. Quantum numbers are the layers. The second quantum number is the inclination or the longitude angle. And the third quantum number is latitude, the reverse azimuth. Sometimes they use a fancy word, okay? And that's how many get spread evenly along that same latitude. And then the fourth quantum number is which hemisphere you're in. Remember, you have a poly pair, hemisphere pair at this position, always this. Remember, if this is on 0, this will be at 180 degrees. It's a half phase off, because if you put two layers together, if they're like this, if you can do this and rotate them a half phase, they can fit together tighter because they're all pulled into that Bohr radius wall at the uh, um, towards the nucleus. So as a result, you get quantum numbers that go 0. That second quantum number starts at 0 because it's at the pole. There's no inclination angle. And then you have 1, 2, or 3. So you sort of have to divide the 90 degrees by 2.5 to get where those are. And here you have to divide it by um, 3.5. So it's 28, 56, 72, whatever, uh, going on. But 0, 1, 2, 3. And then those hemisphere counts are the meridian and then each direction from it, plus and minus. And finally, that interlacing, you can see here, this is a famous early picture of electron subshells. Shell 1 is right there in the middle and very difficult to see, but shell 2 and shell 3 are close together. Shell 4 and shell 5 are close together. That is this interlacing where the first layer may be at the 0 degrees, but a second layer in the same hemisphere can fit tightly before having to go to the next layer. So 1 in each hemisphere times 2 hemispheres. 3 times 2 is 6, subshell D offset, and so you get shell 2 and shell 3 have the same counts, and then shell 4 and shell 5 have the same counts. As you build, the periodic table becomes 2 times the squares, pi r squared. So you have a circle. A circle is the tightest configuration in 2 dimensions. And that is overlaid because the third dimension is the basic two sets of hemispheres. So 2 for one hemisphere, the squared for pi r squared equals 2, 8, 8, interlacing, 18, 18, 32. That is your periodic table of element described from this simple three forces, free to rotate, but with a frame of reference of that nucleostatic axis.